too much copying and pasting in the web page. Okay, so we're back on the normal schedule, such as it is. There are basically 3.5 more weeks of class. Okay, which means that's not including Thanksgiving week. There are going to be 3 more homeworks. There's homework 9, which is out now. Homework 10, which will release next Tuesday and will be due the Tuesday after break. And homework 11, which will be released on that Tuesday and will be due on the very last day of class. There is some question every semester whether we can reasonably get the last homework graded and back to you in time. Right now, things look pretty good. We've been keeping up with the grading on time. So my guess is that homework 11 will be able to grade and at least in principle have available for everybody to pick back up again the following Friday so that everybody gets feedback at least a few days before the exam, which is on Tuesday, 5 weeks from today. So homework 9 is out. The link on the front of the web page is currently broken. I'll fix that immediately after class. But if you go to the page, there's a separate page that just lists all the homeworks and with pointers to solutions and such. That link is correct. You'll notice there are only 2 required problems on here. The reason that there are only 2 is not, I think, because these 2 problems are hard so much as they are going to be long. This is, both of these questions start with design a Turing machine to do something, which means at some level you're really doing an MP. You're writing code. There are some details. The answers are likely to be pretty long. It's going to take a fair amount of time to actually get the bugs worked out, especially because you're doing it on paper. You don't have a compiler to argue against. So please start on this early. There are now Turing Machine notes on the web page, both mine and Lenny's slides that he used last semester when we taught this material. The notes that I've written are, this is the first time I've taught the material myself, so the notes are still somewhat incomplete and probably have bugs in them, so please read them carefully and please let me know if you find any mistakes. We're chugging through grading midterm 2. Our goal is to try to get those back into your hands by the lab on Friday, but certainly we will get them back to you no later than Wednesday. Okay? And hopefully also by Friday, I'll be able to say something about actually how everybody did, as opposed to apparently how everybody thinks they did. So we can see whether I actually really need to panic or just be concerned. And they use that pronoun carefully. So the scuttlebutt that I've heard was, that was hard. And the way they usually measure this is there's always, normally in 473 at least, there's always a few people who say midterm 1 was easier than midterm 2, and a few people that say midterm 2 is easier than midterm 1. And it's always non-zero on both sides. This time, no. Did anybody think midterm 2 was easier than midterm 1? Okay, we have a half-hearted, yeah, okay. So it was harder. But remember that the course is graded on a curve. So if everybody did worse, then nobody did worse. And if it really looks like the scores just kind of went way down below what we saw in midterm 1, that's more of an indication that we're doing something wrong. I'm doing something wrong in how we're teaching the material, how we're organizing the course, how we're, structuring the labs and the homeworks and the lectures, and less a reflection on your ability, which means we will need to do some adjustment at the end of the semester to weigh that midterm less. Okay. So however it comes out when we actually have the numbers in front of us, I'll do my best to be fair and reasonable, even if the exam turns out to not have been fair and reasonable. Okay. So, for the last couple of lectures, we've been talking about this bizarre model of computation called the Turing Machine. And the basic picture of a Turing machine is that you have a device which can be in any number of a finite number of states. So there's some finite set Q that describes the internal state of this device. And the device has access to an infinite tape, which it can think of as memory, and written on that tape are some arbitrary symbols from some finite alphabet. And in any single step of execution, what happens is the Turing machine reads a single symbol from the tape based on whatever symbol is at the current position of the read-write head. Think of it really as the position of the machine on the tape. And then based on its internal state and the symbol it reads, it changes its internal state, it changes the symbol on the tape, and it moves the head either one step to the left or one step to the right. Okay? So if I started in state Q, then after reading the symbol 0, I might end up in state R, and all these symbols are going to be the same, except this one. Okay, so based on some internal rules stored in the machine, when I'm in state Q and I read a 0, the instructions say change to state R, write an @ and move one step to the right. Okay? Now, the surprising thing about these Turing machines, at least when you first see them, is despite the fact that the computation is extraordinarily limited, the Turing machines really seem to capture completely the notion of what people or machines can actually compute. Right? So the metaphor that Turing used was that each of these cells is a sheet of paper, and the internal state of the machine is the internal state of some human being's brain. And as long as I'm staring at a particular sheet of paper, I can erase and write whatever I want on that sheet of paper. But eventually, I may need to remember some stuff, turn the page, and write on a different sheet of paper. And the idea of allowing myself only local access just models the fact that I can only really work with one sheet of paper at a time, and I can only have so many pieces of paper on the desk at a time. But you can simulate much more complicated things. Right? So there were, on last week, we discussed extensions of this model that allow more complicated behavior or that allow more complicated structure of memory. So, for example, you can allow a doubly infinite tape. Instead of having the tape end on the left, you can have it extend infinitely to the left, and this doesn't increase the computational power of what the machine can do. You can allow multiple tracks, meaning that in every cell of the machine, I don't store one symbol, but I can store, say, 5 symbols. I can allow multiple read-write heads, meaning that I have, say, 6 places where I can look at the tape at every iteration, and the evolution of the machine depends on my internal state and the 6 characters I read. And the transition function tells me, based on my state and those 6 characters, what is my new state, what 6 characters should I write onto the tape in those locations, and for each of these heads, should I move it left or right? You can allow for multiple independent tapes. So for example, I could insist, with no change in the power of the Turing machine that I construct, that the input lives on a read-only tape over here, and then I have this work tape. And in fact, maybe I have 5 work tapes, and the 3rd work tape has 7 tracks and 22 heads. Right? And then I have a write-only output tape where I'm going to put the output of the computation. Having these additional resources doesn't change what things the Turing machine can compute. It doesn't change which languages the Turing machine can recognize. It doesn't change what functions from set strings to strings the Turing machine can compute. With a little bit more care, you can allow subroutines, including recursion, by treating one of the tapes as the call stack and doing exactly what you do on a real machine when you call a subroutine. You put a stack frame onto the stack with a return address underneath it. And then you pretend that that stack frame, anything below the bottom of the stack frame is completely inaccessible, except maybe through indirection, which you can also simulate. You can allow your machines to have random access memory in the sense that I imagine that as a basic step of the Turing machine, after writing an address onto an address tape, I invoke some action that magically retrieves the corresponding data and writes it onto the data tape. Or I write an address onto the address tape and data onto the data tape, and then I go to some special state that magically stores that data at that address. And now the behavior looks, once you have subroutines in random access memory, it's hopefully believable that anything you can do with the first 2/3 of this course, you could do with the Turing machine. Any dynamic programming algorithm ultimately is a bunch of loops with a bunch of memory accesses. Any divide and conquer algorithm is ultimately a bunch of recursive calls possibly accessing some array, right? And so if I wanted to do binary search, I could implement that by using random access to pull something out of the input array and using the recursive subroutine to actually do the search. Okay, so
finite?
So I wanted to, this is a good point, and it brings up a subtlety in the definitions of the model. It is true that Turing machines have an infinite amount of memory. On the other hand, either the Turing machine runs forever, or it only ever accesses a finite amount of its tape. So it's actually a bit more accurate to say Turing machines have a finite but unbounded amount of memory. If you run out of space, you can just glue on more tape, which is similar to a real computer. If I run out of disk space, I can just plug in another disk. Okay? You can push this argument further and say, well, no, actually in the real world, there are a finite number of elementary particles, and therefore I really do only have a finite amount of storage available to me in the universe. At which point I say, well, yeah, it's true. This is true. In that sense, it follows that anything you can do with a real computer, because really you do have a finite amount of memory, is equivalent to a finite state machine. But this metaphor is not useful, right? When you're writing code, except in some very limited circumstances where you really do have to worry about it, most of the time you write code as though you have an infinite amount of memory. The machine that you're programming has an infinite, or at least an unbounded amount of memory, right? Now, if what you're writing is a memory manager, of course that's not true, okay? You have to keep yourself within some small constraints, and you have to worry about moving things. But even then, with memory management, you're really, even writing a paging algorithm, you generally assume that you have an infinite amount of disk space, and only a finite portion of it is in memory, in which case the disk is really what I'm calling the tape, and the memory is part of the internal state, right? So, strictly, if you think about things in terms of physics, yes, memory is limited. But thinking about things in terms of physics is useful only if you're a physicist, right? We want, as much as possible, to think about things in terms of some mathematical abstraction. Even physicists do this by assuming, for example, that relativity and quantum mechanics doesn't matter when they build a bridge, right? Because it's more useful. We can actually make predictions about how computation is going to behave based on this metaphor of infinite memory, and more often than not, those predictions will pan out. Right? Okay. So there's one more extension to the Turing machine model that I want to talk about today, which is of a fundamentally different character than the things that I've talked about so far. I mean, one of the things that, if you push through the details of how these various simulation results work, what you end up with as a theorem is that any algorithm that runs in t steps on a random access machine, meaning, for example, your wristwatch or Blue Waters, can be simulated by a standard Turing machine, meaning a Turing machine with one head, one tape, one track, binary tape alphabet, if you like, in not too horrible number of steps. Okay? So T steps of operation on a quote-unquote real computer or a realistic computer can be simulated on a Turing machine in roughly T cubed steps, T cubed transitions. Okay? Now, part of where this T cubed comes from is in the way that you implement multiple tracks. and part of it comes from the way we implement random access memory. So I'll show you where one of the extra factors of t comes from, which is if I want to imagine, sorry, not multiple tracks, but multiple heads. If I want to imagine a machine that has two heads, the way that I simulate this using a machine that only has one head is essentially, I think of these now as just marks on the tape. And my actual Turing machine head is going to go like this, and then back, and then like this, and then back, and like this, and back, and then like this, and then back. So here I'm doing a read, here I'm doing a write. And so one step of this two-head Turing machine is being simulated by a whole bunch of steps of the one-head Turing machine. Yes? It doesn't. I mean, if you really want to be careful about it, you only have to go back and forth. But then you have to remember, is my other head to my left or my right? This is more bookkeeping, right? But the main observation is this distance is less than, is at most t. Remember, at the very beginning, the Turing machine starts with all heads at the left end of the tape. So after t steps, each of those heads can be at most t steps away from the beginning of the tape. So each of these scans, whether I do it all the way back to the left or whether I go back and forth, each of these scans takes me order t time. So altogether, one step with two heads takes me order t steps with only one head. Okay, so this gives me one blow up of a factor of t. Right, and I won't go through the other one for doing random access, but essentially it boils down to observing that in order to look up an address, I have to have one head here and one head here scanning, and I have to go back and forth checking what the addresses are equal or not, which requires me to have multiple heads. So I'm doing a scan, which takes order t time, but each of those time steps is multiplied by another order t. Okay? So the punchline from this is, if I'm only worried about efficiency up to whether the running time is a polynomial or not, Turing machines are perfectly fine, right? Now, the types of problems that I'm interested in here, so the set P, this is the set of all languages that can be decided in polynomial time on a Turing machine. What this means is on input W, there is a Turing machine that accepts W if and only if W is in L, and it rejects W if and only if W is not in L, and the running time of the algorithm is big O of the length of W to some constant C. Okay, that's what it means for a Turing machine to decide a language in polynomial time. So, for example, when I say decide a language, this is equivalent to saying any yes/no problem that problems that can be solved in polynomial time. So, for example, I can give you an array and ask you, is it sorted? You can write a for loop, for I equals 1 to n, compare ai to ai plus 1. If anything's out of order, return no. If everything's in order, return yes. Okay, so that is a polynomial time algorithm for a decision problem. It's also a decision algorithm for a language. The language contains all arrays that are in sorted order, and none of the arrays that are not in sorted order, thinking of them as sequences of bits. Right? So at a very, very crude level, if I'm trying to decide whether a problem can be solved efficiently or not, the barrier that people have settled on is whether I can get a running time of the form order n squared, order n cubed, order n to the fourth if you're really generous. But I want to avoid running times of the form 2 to the n. I want to avoid exponential running times because if n is even remotely large, those are going to explode. A polynomial is better because if I double the size of the input, I'm only going to increase the running time by some constant factor. Right? All right, so this is this set of languages called P. And what this statement about Turing machines and simulation says is, for purposes of this crude classification of problems into efficient, meaning polynomial time, and inefficient, meaning something bigger, I can think about Turing machines, or I can think about RAMs, or it doesn't matter. Okay. By the end of the lecture, I'll tell you what NP is, and then I can pose the $1 million problem. Okay. Okay. So the further extension that I want to make is one that we made earlier with finite state machines. So if you remember, there were two kinds of finite state automata. There were deterministic finite state machines, and there were non-deterministic finite state machines. In a deterministic finite state machine, the evolution of the machine is completely determined by the input string. If I see a 1, I branch this way, then I see a 0, I branch that way, I see a 1, I loop, I see a 0, I branch down, accept or reject. I have no choice. If I run the machine again, it's going to do exactly the same thing. A non-deterministic finite state machine, I had choices about what to do. So there was this standard example, 0, 1, 1, 0, 0, 1, 0, 1. This is an NFA that accepts the language of all strings that contain either 1, 1 or contain 0, 0. Right? And notice you've got a choice at the beginning. Whenever I read a 0 and I'm in this initial state, I have a choice. Do I stay put or do I branch? And one of the fundamental things that we showed about NFAs and DFAs is they both accept the same languages. Any DFA automatically is an NFA, and any NFA can be simulated by a DFA, possibly with exponentially many more states. Okay, so this is an old theorem that we proved before. A language is accepted by DFA if and only if it's accepted by an NFA. So these two models of computation have exactly the same computational power. They can decide the same yes-no questions. Is this string in this language or not? On the other hand, but DFAs may have, exponentially more states than the equivalent NFAs. Right? So if the question, in particular, if the question I'm asking is, here's a string of bits, let's look at the 10th bit from the end and accept the string if that 10th bit from the end is a 1. It's pretty easy to come up with an NFA that has only 10 states. Right? Basically, the 10 states are the start state and the states you go through to read the last 9 symbols. And you just decide non-deterministically, oh, I've hit the 10th one, let me go ahead and branch. But any DFA for the same language needs at least 1,024 states. Okay? So the transformation between NFA and DFA involves an exponential explosion in the number of states in the worst case. There's a similar possibility for Turing machines. So far, we've only considered Turing machines that are deterministic. The behavior of the machine, when I'm in a certain state and reading a certain symbol, is completely determined by that state and that symbol. When I'm in state Q and I read a 0, I must write an at, change my state to R, and move one step to the right. It's determined ultimately by this transition function based on the input to into the machine. So just as we defined non-deterministic finite state machines as having a choice about what to do, we can define non-deterministic Turing machines as having choices about what to do. So a non-deterministic Turing machine, intuitively, the result of the transition function isn't just one triple that says new state, new symbol, left or right, but rather it's a set, let's say +1, and then maybe it goes to RC -1, maybe it goes to SD +1, and then maybe it goes also RB +1. Okay, so instead of everything being completely determined, I now have choice built into my model. Okay, and in fact, Turing himself referred to these as choice machines. Okay. So formally, this means that my transition function has this bizarre signature. Okay. Given a state and a symbol on the tape, I return a set of triples, each of which contains a state, a tape symbol, and +or -1. If this confuses you, look up above the line. Right? It just means you get a set. Okay. So right at each step, if I'm in state Q and I read symbol A, then I choose some triple out of this set, Q prime, QA, and then change the state to Q prime, change the symbol under the tape to B, and move the head left or right, depending on this one. If this set happens to be empty, then I just immediately halt and reject. Okay? So that's what it means for a Turing machine to be non-deterministic. Is instead of having a single predetermined action for every state symbol pair, I have a set of possible actions, and in principle, the machine can freely choose any of them. Okay? Just like in NFA. Yeah. What? Magic, voodoo, arbitrary, don't care. Right? Now, how do we answer that question for NFAs? How do NFAs choose which way they branch? They try them all. Okay? One version of non-determinism is you create parallel universes where in each parallel universe you make a different choice. Right? And if a particular sequence of choices leads to rejection, you just pretend that universe never existed. Another way of thinking of it is you launch not parallel universes, but parallel execution threads. And as long as one of these threads eventually leads to an accept, you accept. Yet another one, and I'll come back to this a little later, is that it happens by magic. If it is possible to do so, every time the Turing machine faces a choice, a little birdie flies down and lands on your shoulder and goes, tweet, 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 take that one. And the little birdie always leads you to an accepting configuration if there is a way to get to an accepting configuration. Okay? It's exactly the same set of metaphors that we used for NFAs. Right? All right. So I'm going to say that a non-deterministic Turing machine M accepts a string W if there is some sequence of choices that leads from the initial configuration where I'm in the start state, I have the string W on the tape and my head is at position 0, to some configuration that has the accept state. Okay? This is exactly the same as the conditions under which an NFA accepts a string. An NFA accepts a string if there is a series of decisions that are consistent with the transition function that walks from the start state to an accepting state. Okay? Now, however, if you remember, there are 3 different ways. I'm sorry, there's a question back here.
I know in my intuition.
Mm-hmm.
And I imagine it's something to do with the track of memory.
Yes.
How does that manifest itself to be more powerful?
So there are simple languages that, like 0 to the n, 1 to the n, that there's provably no regular, it's not regular, there's no DFA or no NFA that accepts them. On the other hand, because you can write code that it decides whether a string starts with some number of zeros and ends with the same number of ones, there is a Turing machine that can decide that language. Now, I'm not sure that that's a sufficient answer to why, right? It's a proof that there are things Turing machines can do that DFAs can't. The closest I can say to intuition about why Turing machines are more powerful is that DFAs necessarily have a bounded amount of memory. They can only remember things in their internal states. Whereas a Turing machine has an unbounded amount of memory. Can write as many symbols as it wants or needs onto the tape as long as it eventually halts. And so the distinction is between what you can keep in your head and what you can do with an infinite supply of paper. Okay. Now, there are 3 ways for a deterministic Turing machine to behave when it receives a string as input. It can eventually reach an accept state, and then it halts and it accepts the string. It can eventually reach the reject state, and it halts and it rejects the string. And other. The other is essentially, it loops forever. I don't know whether this string is accepted or not because the machine hasn't halted yet. Okay? And because there is this third option of looping forever, there's necessarily some asymmetry in the definition for non-deterministic machines between what it means for it to accept and what it means to reject. So a non-deterministic machine accepts if there is a sequence of choices that leads to acceptance. A non-deterministic machine M rejects W if every sequence of choices leads from the starting configuration to a reject state. Okay? So, horrible joke, but it will help you remember this. It's easy to think of yourself as being acceptable if one person accepts you. But in order to think of yourself as unacceptable, everyone in the world has to reject you. Okay? As long as there's one person who hasn't answered, you think maybe, and then so you just don't know. So you neither, smile because you're accepted or frown because you're rejected. So in order to be accepted, only one choice has to lead you to an acceptance. But to reject, all choices have to be bad. Okay? Which means, of course, that even for a non-deterministic Turing machine, there are three ways to respond. If there is a sequence of choices that leads to an infinite loop, then the non-deterministic Turing machine does not accept, and it does not reject. It might accept. So one way to think about how this works is imagine that you treat the execution of the Turing machine, this non-deterministic Turing machine, as what's called the decision tree. Right? So I'm going to have a node in the decision tree that corresponds to as much evolution of the machine as I can do without having to make a choice, without having to make a decision. And then at some point I have to decide, do I change to state Q or to state R? Do I write an X here or a Y? Do I move the head left or do I move the head right? And then I've spawned two parallel threads or two parallel universes. Right? And then later in this execution, each of these may branch, and then later each of these may branch. Okay? So a decision tree that leads to acceptance is one where there's some path in this decision tree that leads to an accepting configuration. Now, it doesn't matter whether the other configuration, the other paths lead to no's, or if the other paths lead off to infinity. Right? This is still a description of an accepting computation by a non-deterministic machine. Okay? A rejecting computation by a non-deterministic machine, every path leads to a leaf labeled no. Okay. Okay. So, everybody understand what it means for a non-deterministic machine to accept or reject? Okay. Now, the two things that I would like to be able to show is for any non-deterministic Turing machine M, there is a deterministic Turing machine M prime such that M accepts the string W if and only if M prime accepts W. M rejects W if and only if M prime rejects W. Right? So they accept and reject. For any non-deterministic machine, there's an equivalent deterministic machine, meaning it accepts the same strings and it rejects the same strings. But if M runs in, say, t of n time, M prime may need something like 2 to the t of n time. Okay, so just like when I went from NFAs to DFAs, I didn't change the languages that they can decide. If a language is regular, it has a DFA and it has an NFA. If a language is not regular, then it doesn't have either. Similarly here, what I want to argue is if a language is decidable by a non-deterministic machine, it's also decidable by a deterministic machine. Okay? Just same acceptance and rejection. On the other hand, when we went from NFAs to DFAs, there was this sometimes you might have to explode the number of states exponentially. Remember, the states is the only resource we really have when we're talking about DFAs. Yeah? Omega of t to the n. This is the, big O means less than or equal to some constant. Big omega means greater than or equal to some constant. Just think of this as greater than or equal, but there may be a factor of a million in there that I don't care about. Okay. So for Turing machines, I can't argue that the number of states is going to blow up because there's a universal Turing machine that has 7 states and 5 tape symbols. So anything that can be computed with 7 states and 5 tape symbols. Okay. The other resource that I have available to me, what could possibly change, is the amount of time I need. Okay. So intuitively, what I would like to argue is that this reduction from non-deterministic machines to deterministic ones doesn't change the power of the machine model in terms of what it can compute, but it does blow up the running time, right? Now, I can change this statement slightly. Okay, to actually make a big O statement, an upper bound, that exponential is the worst that I could possibly need. So I will actually show you how to simulate a non-deterministic Turing machine by a deterministic one with only exponential slowdown. And what I would like to say is this is the best possible. Unfortunately, if I could say that, I'd be a millionaire. Okay? This is the P versus NP problem in a nutshell. All right? The P versus NP problem is saying, we all believe that solving problems with no help, that's what a deterministic machine does, is harder than solving problems with help. This is the non-deterministic model where a magical little birdie lands on your shoulder and always tells you the right thing to do. Obviously, it's easier to solve the homework problems if you already have the solutions in front of you. Right? Obviously, it's easier for me to convince you that something is true and have you thoroughly check every assertion I ever make, than it is for me to just say, prove this is true. Obviously. Okay? We don't have a proof of this fact. Right? And at some level, the fact that we don't have a proof of this fact is evidence for this fact. If we had a proof of this fact, presumably it would be easy for a human to read. It would be possible for a human to read. So if it were just as easy to come up with the proof as it is to read it, we would have already done it by now. Okay, that's not really a proof. Okay. So what I'd love to be able to say, just like I can say for NFAs, is this the non-determinism is really incredibly powerful. It allows you to shave, turn exponential things down into only polynomial things. But I don't actually know that that's true, right? So I'll come back to this proof in a second, but I want to give you some reason to believe why intuitively why this might be the right thing to expect. So let me give you an example of a yes-no problem. And we'll see this again later. This is called the three-coloring problem for graphs. Okay, so I'm going to draw a graph here on the slide. And three-coloring for the graph assigns a color to every node with the property that if two nodes are adjacent, then they have different colors. Okay? So here is a graph that has 6 nodes, and I successfully colored it with 3 colors. 2 nodes that are yellow, 2 nodes that are pink, 2 nodes that are green. Okay? So the three-coloring graphs question is, given a graph G, is it three-colorable? Is there a way of assigning these colors so that every node, the 2 colors, every edge, the 2 colors at the ends are different? Okay? How would you solve this problem? Don't be clever. Sorry? Okay. But when we're thinking about dynamic programming, what is, dynamic programming is an efficient implementation of something. Backtracking, right? So I could imagine saying, well, let's suppose I don't know what color this is. Let me try all possible colors. And then on the next node, I don't know what color this is. Let me try all possible colors. Oh, it better not be yellow if I'm in the yellow part of the world. And then when I'm here, well, once I've decided this one is determined. But in principle, this one might be, have 2 different colors. So I get this backtracking algorithm, right? And in fact, that's basically the best we know how to do. There's no opportunity for memoization here because the choices I make about what colors I'm going to use for future vertices depend on the choices I've already made for previous vertices. So when I recurse, it's more like the Queen's problem. I have to remember all the colors I've assigned already in order to decide what colors I might assign up ahead. So there's a nice deterministic algorithm which essentially just tries all possible colorings and then checks to see whether that coloring is legal. And okay, maybe with a little bit more effort you can bring this down by noticing that if you're next to a vertex that's already been assigned a color, then you can only have 2 colors. So you get 2 to the v instead of 3 to the v. But that's really the best that you could possibly hope for. Okay, now I'm going to give you a non-deterministic algorithm, which you could implement on a non-deterministic machine, and that would decide this problem in polynomial time. I guess that this one is yellow. I guess that this one is green. I guess that this one is pink. I guess that this one is yellow. I guess that this one is pink. I guess that this one is green. Hey, look, I had a 3 coloring. Yay! Now my guess is, every time I said I guessed that this one was green, you didn't notice, but in fact I generated 3 parallel universes, where in one of them I said I guessed green, in one of them I said I guessed pink, and one of them I guessed yellow. But conveniently, all of the universes where I ended up with an illegal 3 coloring, I blew up the universe. Right? Yay, we survived. So if I wanted a non-deterministic algorithm, I just guess the colors, and then I need, I don't know, order E extra time. Because for each edge, I need to look up the colors on the ends and verify. Okay? Now, if I'm given a graph that isn't 3-colorable, this algorithm will still non-deterministic algorithm will still end after a linear amount of time. So I'll guess this one is red, I'll guess this one is blue, I'll guess this one is green, I'll guess this one is boom. But in all computation branches, I will realize that I've reached an inconsistent state and destroyed the universe after only a small number of steps, nowhere near the exponential time that I need. Okay, so here's a problem where if I had this magic non-determinism fairy that would sit on my shoulder and tell me what colors to pick, then I could solve this problem really fast. But in the real world, the best I know how to do is some exponential backtracking stuff. Okay? Now, going from a non-deterministic machine to a deterministic machine, essentially what I'm going to do is a backtracking search over all possible things the little birdie can tell me. Maybe the little birdie says blue. Does that work? Okay, that didn't work. Maybe the little birdie says red. Did that work? Well, I don't know. In the next step, the little birdie said blue. And did that work? Well, no. Okay, so back up. All right, so I need to do a kind of backtracking search to consider all possible sequences of choices. Yes?
Was the tricoloring
The algorithm, yes. But there might, in principle, be a faster algorithm lying under a rock in Tibet that runs in polynomial time. No one believes that this is true. Even the people who've been to Tibet and looked for it. But it might be true. Okay. Okay. So let me formalize this by describing a different way of thinking about non-deterministic machines. Okay. So I'm going to think of an NTM is really a deterministic Turing machine with two input tapes. But you only get to see one of them. Okay, so I'm going to have my input X, and I'm going to have some other input Y, and I'm going to have a work tape. Okay? Now, when you invoke this machine, you write your input here. And then you say, hey, little birdie who is going to land on my shoulder while I'm doing the computation, you know everything. So in particular, you already know when I'm going to need to make various decisions based on the transition function and the string that's put on the input tape. So why don't you just write all those down, and then you can go off to Tibet or whatever. Okay? So the little birdie magically writes down some other string on what I'll call the advice tape. Okay? Now, at every transition now, I look at my current state, and I'm looking at some symbol on the work tape, some symbol on the input tape, and some symbol on the advice tape. And based on that state in those three symbols, I decide to write something onto the work tape and to move advice to the right and move input to the right and possibly move around on the tape, on the work tape. Okay? So this is supplied by magic. Okay? And the only thing that I'm really changing here from the original non-deterministic Turing machine model is instead of saying, oh, I got to this state with the symbol, I have a choice, I'm resolving that choice by saying, I got to this state in the symbol, and the advice tape gives me another symbol. And based on that advice, my choices are, I don't have any choice anymore. I will do what the advice tape tells me to do. Okay? So again, if I want to imagine the execution of this machine, the decision tree here is I read a 0 from the advice tape versus I read a 1 from the advice tape. And then I branch. I read a 0, I read a 1, I read a 0, I read a 1, I read a 0, I read a 1, and so on. Okay? So if you prefer to think of it as I get to a configuration where I have a choice, and then a little birdie lands on my shoulder, fine. But I'm claiming that I can implement that little birdie by just having another tape. And the little birdie just leaves droppings or doesn't leave droppings into the cells of that other tape. And so you look at the tape instead of actually having the birdie poop on your shoulder. Okay? Otherwise, it's not really, nothing is any different. And now I say that, M accepts a string W. What that actually means is that M accepts the pair WX for some string X, and M rejects W means M rejects the pair WX for all strings X. And really, the intuition that I want you to have here is that W, think of W as a theorem that you want to establish whether it's true or not, and X as a proof. Right? So W, for example, might be a graph, and you want to know whether that graph is three-colorable or not. X is a proof. If there is a proof, namely if there is an assignment of colors, then there's a deterministic Turing machine that checks whether that assignment of colors is really legal. If there is no legal assignment of colors, then no matter what I write on the advice tape, my Turing machine is going to reject. It's going to say, no, that's not valid. No, that's not valid. No, that's not valid. Regardless of what I try to convince you is valid coloring. Okay? So the advice tape, in a sense, is, the input W, this is your homework problem, and the advice tape X is the solution to the homework problem. If there is a solution, then non-deterministically you solve the homework. If there is no solution, in other words, no matter what you turn in, if I give you a 0, then non-deterministically you can't do the homework. Okay? All right. So, how am I going to actually simulate this using a single Turing machine with a single input? And there's no more magic advice, right? So, to simulate with a standard deterministic Turing machine M prime, try all x's. Right? If I want to know whether the graph is three-colorable, I try all possible ways of coloring it. If I want to know whether this non-deterministic Turing machine will ever accept anything, I try all possible sequences of choices. Okay? Now, intuitively, you want to kind of think of this as a backtracking algorithm. And what the backtracking algorithm is doing is actually searching this tree, searching this decision tree to see if it can find a yes leaf. Now, normally, when you do backtracking, you do depth-first search. You say, let me imagine that the first choice is a 0. Let me recursively look for an accepting leaf. And if I don't find one, then I'll go back up and try 1 and then recursively look for an accepting leaf. That's not going to work here. Why not? Because I might have infinite loops. Right? I can't apply depth-first search because it might infinite loop. If the first set of choices I examine lead me down the garden path into a black hole. I'll never return, which means I'll never eventually come back up and find the actual accepting path. So can you suggest perhaps another strategy that I might use to search this tree that avoids this problem? Depth first search didn't work, so breadth first search. All right, so the way breadth first search works is, remember, I look at the tree level by level. And as soon as I get to a level that has a yes, I stop. Yeah. I'm sorry? Then the simulation will run on forever, which is the right thing to happen. Right? Remember what the three options are. If there's an accept leaf at some finite depth, that means there's a set of choices that leads me to an accept state, then I want to accept. If every path leads me to a reject state, then this tree is finite, and eventually BFS will terminate, and I've only seen no leaves, and so I'll correctly reject. If this tree is infinite, then the right thing for me to do is infinite loop. I can't accept, and I can't reject, because maybe there's something a little further down that branch I just haven't seen yet. Okay? So I want to try to do a breadth first search of this recursion tree. Well, how am I going to do that? Okay. And the way that I want to think about doing this is I'm going to first consider all strings of advice that are 1 bit long. That'll get me to the first level. Then I'm going to consider all strings of advice that are 2 bits long. Then I'm going to consider all strings of advice that are 3 bits long. Okay? So the way my simulation is going to work is the following. For L goes from 0 to infinity. For all strings X in whatever my advice alphabet, I guess it's 0 to 1. Okay? Run my machine with the input W and the advice X. Okay? Now I'm going to make one further restriction here, which is that I'm going to insist that at every step of execution of M, I have to consume one piece of advice. I always have to, at every step when I'm looking at the advice tape, at every step I move to the right. I may or may not actually use the advice, but it's there. I have to listen to it. You have to sit there and listen to me blather at you for 90 minutes. Whether or not you actually use the information that I'm giving you, that's up to you. Okay? Another way of saying this is I'm going to run the algorithm, but I'm going to stop after so many steps. I'm going to set an alarm clock, and once I've run for the number of steps that I could possibly run with that many bits, I'm going to stop, and either I've already accepted, in which case, great, I'm done. I've already rejected, in which case, maybe I'm done. Or that I still have more computation to do, but I'll come back. And later I'll consider the advice string x1. Right? So later I'll examine, longer branches in the computation tree. Right? If M on if M accepts on WX, then I accept. Okay, so this means that I need some sort of counter, which I can implement on a separate tape. As just every so often, I write another 1 on my counter tape. Here, I need to be able to enumerate, I need to be able to add 1 to a binary number. All right? You can imagine writing a program that will add 1 to a binary number. Do that with a Turing machine. And that will automatically cycle through all possible strings of a given length. Okay? So this is just add one over and over again. This we know how to do because it's a Turing machine. It's given to, M is given to us. So you can just basically just call it as a subroutine. Right? And so I claim and if everything, if everyone rejects, then reject. So if I ever get to a state, I guess I need to put that here. If I ever get to a state where all advice strings of length L lead to a reject state, then at that point I know the correct answer is to reject. Okay. Now, I claim that this solves the problem that M solves. This algorithm, which I can encode as a Turing machine M prime, it's deterministic and has one tape and one head and all that stuff, accepts a string if and only if the non-deterministic machine M accepts the string. And basically the reason is if there is an advice string that accepts, I will eventually find it because I'm really considering all possible strings. And if there is no advice string or if every advice string leads me to a reject, eventually the strings I'm considering in this loop are long enough that I'll have searched the entire tree. On the other hand, the running time of the algorithm, right? If the non-deterministic Turing machine M runs in t steps, this t is really L, right? This is how many steps I need to run, and so the set of advice strings that I need to look at have length t. So the advice has length at most t, which means that I might, in my deterministic Turing machine, might need to consider 2 to the t different advice strings. Okay, so I do get an exponential blow-up, because if I needed the little birdie to sit on my shoulder 100 times, I have to consider all possible strings of 100 bits. Okay? So anything a non-deterministic Turing machine can do, a deterministic machine can do, possibly with an exponential blow-up in time. Now, the NP, and I'll be done, this is the set of languages that can be decided. Where did I put the definition of P? I want to mirror the language exactly. Well, sorry. By a non-deterministic Turing machine in polynomial time, meaning that given a string W, if W is in the language L, then MWX accepts for some x in time as of W to the C. And if W is not in L, then M of WX rejects for all strings x, again in time length of W to the C. Okay. So P is things where I can answer yes, no quickly. NP are the things where if the answer is yes, I can convince you quickly. But in any case, no matter what guess I try to convince you of, you'll either believe me or not in polynomial time. And the million-dollar question that we don't have an answer to is, are these two the same thing? All right, we'll say more about this on Thursday. Thank you.